Hi, this is Dr. John Bergduff. In this video, I want to show you how to solve an inequality that involves radicals using graphing. Now that might mean using a graphing utility such as a program or a graphing calculator, or it might even simply mean graphing by hand. Here's an example of a radical inequality. Very simply, an inequality that has a radical in it. And here's how we're going to solve that inequality. First of all, we're going to solve the underlying equation. So if you look at what happened here, I simply took the greater than or equal to in the inequality and replaced it with an equal sign for reasons which will become clear later. Now, in other videos, I show you how to solve a radical equation. So this one I'm going to do fairly quickly. You might want to refer to one of the other videos if you need a little bit more help. So in order to solve a radical equation, it is often much easier if you can first of all isolate the radical. What I simply would mean by that is to subtract the 3 from both sides to give me the effect of having the radical by itself. That will make it easier to do the next step, which is to eliminate the radical by raising both sides to a power. The principle of balance that I sometimes talk about applies here, that if you perform the same mathematical operation on both sides of the equation, it should be the case that the solutions are not changed. So squaring a square root will make the radical go away, and as long as we do that on both sides, we should be all right. Now, squaring a square root would simply give me the radicand, the quantity under the radical, on the left. On the right side, though, I would have to think about squaring x minus 3, which means multiplying x minus 3 times itself, using the FOIL rule or the formula for the square of a binomial, but I'll use the FOIL rule here. Product of the first terms is x squared. Product of the outside terms is negative 3x. Product of the inside terms is negative 3x. Product of the last terms is 9. And combining some like terms, we would get x squared minus 6x plus 9. The radical equation has now simply become a quadratic equation. I can continue to solve it by subtracting x from both sides, which would give me negative 1 equals x squared minus 7x plus 9. And then adding a 1 to both sides to get a 0, x squared minus 7x plus 10. That quadratic equation could be solved by the quadratic formula or very simply by factoring. It factors nicely. It is simply going to be x minus 5 times x minus 2, looking for two numbers that multiply to give you 10 and add to give you negative 7. So let me go to a fresh page here. This is where we're at right now. 0 equals x minus 5 times x minus 2. I set the two factors equal to 0, as I would ordinarily do with a quadratic equation, and that gives me x equal 5 and x equal 2. We do need to remember, though, that radical equations can give you false solutions. Radical equations can give false solutions. So when you get possible solutions to a radical equation, you do have to check them. So we're going to check both of those in the original equation. The original equation, in case you didn't remember, is the following. It was the square root of x minus 1 plus 3 is equal to x. So if I first of all check the 5, take my inequality, everywhere you see an x, replace it with a 5. So we have square root of 5 minus 1 plus 3 equals, again, replace the x with the 5. Square root of 5 minus 1 is 4. Square root of 4 plus 3, square root of 4 is 2. 2 plus 3 equals 5. Bingo, that works just fine. On the same screen over here, and let me change colors back in just a minute here, let's also check x equal 2. So if I go back to my equation and substitute 2, we'd have 2 minus 1 under the radical plus 3 is equal to, and replacing the x with 2 again, that would give me a 2. The square root of 2 minus 1 would be the square root of 1. Is the square root of 1 plus 3 equal to 2? Is 1 plus 3 equal to 2? No, it's not. So indeed we have a false solution, and that simply means we need to throw it away. There's only one valid solution to this equation, and that is 5. And that's all well and good, but that has solved the equation, not the inequality. What can we do from there? So the next step is going to be to sketch the graphs of the functions defined by the two sides of the inequality. Notice here that what I'm calling f of x is the left side of this inequality, and what I'm calling g of x is the right side of the inequality. Those individually can be thought of as functions, and you can graph them by hand, which is totally fine. But I graphed them using Desmos, a computer program that's free that draws beautiful graphs. The red graph here is the graph of the function I've defined by f, and the blue graph is the graph defined by g. And you may recognize those from past experience graphing. These two functions cross each other, and if you look very carefully, where they cross each other is at a point where the x value, if I drop a line right here, is 5. Guess what? 5 was the solution of the underlying equation. The solution of the equation is the x-intercept of the point where the two functions cross. Let me say that again because it's so very important. The solutions of the underlying radical equation represent the x-coordinates of the points where the two functions cross. Now, why is that important? If we think about inequality, and we think about f of x and g of x, which I'm just going to write here, the left side is f of x, the right side is g of x. Remembering that values of f of x are y values, and also values of g of x, what that inequality is really simply saying is, what are the values of x where the function defined by f is greater than or equal to, which would mean, graphically speaking, above the graph of g of x. For what values of x, in this case, for example, is the red graph above the blue graph? We can visualize that from the graph, and that will in fact be the solution of the inequality. If you notice, the red graph, its domain begins at 1, so I am only even defining the red graph beginning at 1, but for an entire interval of numbers between x equal 1 and x equal 5, the graph on the left, that's the square root of x minus 1 plus 3, is above or greater than the graph on the function on the right, g of x equal x. That interval will precisely be the solution of the inequality. The point 1 is included. I'll put a bracket there. And because this says greater than or equal to, the point 5 will also be included. If that had only been a greater than, we would not include that point. And guess what? That is it. By looking at the graph, we see that the function on the left is greater than the function on the right or equal to on the interval from 1 to 5, and that's the solution of the inequality. That's as simple as it is, and I hope that's helpful.